Hello everyone, today is the third lecture in our MRI series of lectures. So let's take a look at the objectives for today. After today's lecture, students will know about image characteristics and the factors affecting image characteristics like spatial resolution, contrast sensitivity, and signal to noise ratio. Students will learn about signals from flow and spatial acquisition techniques that take advantage of signals from flow. We shall also learn about magnetization, contrast, and both exogenous and endogenous contrast agents. MRI images are characterized by their spatial resolution, contrast sensitivity, and signal to noise ratio. We shall look at each of these on the next few slides. Spatial resolution depends on field of view and matrix size, which determines the pixel size, and also on the gradient strength, the sampling bandwidth, and the coil characteristics. In MRI, field of views are on the order of 25 to 50 centimeters, just like in CT. Matrix sizes range from 128 by 128 to 1024 by 1024. In general, MRI can provide spatial resolution approximately equivalent to that of CT, with pixel dimensions on the order of 0.5 millimeters to 1 millimeter for a high contrast object and a reasonably large field of view greater than 25 centimeters. Slice thickness in MRI is usually 5 to 10 millimeters. Spatial resolution can be improved with higher field strength magnets due to higher signal to noise ratio, which means we can use higher sampling rates and thinner slices for a given acquisition, but at the expense of longer T1 relaxation leading to reduced T1 contrast. There is also increased RF absorption and artifacts. Contrast sensitivity is the chief attribute of MRI imaging. Contrast in MRI depends on T1, T2, proton density, and blood flow parameters. MRI contrast agents are based on susceptibility agents that usually create inhomogeneities in the static B0 field that enhance T2 decay or provide a relaxation mechanism to shorten T1 recovery. Contrast sensitivity in MRI is limited by signal to noise ratio and the presence of artifacts. In MRI, signal to noise ratio is dependent on several parameters. These are listed on this slide. The signal to noise ratio depends on the intensity of the signal, the voxel size, the number of signal averages or excitations, and the bandwidth. It also depends on factors associated with the quality of the coils used, the quality and strength of the static B0 field, the slice gap quality, and a factor associated with the reconstruction algorithm. We will look at each of these individually. The intensity of the MRI signal depends on the repetition time TR and the echo time TE. We saw in a previous lecture that the choice of TR and TE affects the contrast weighting that is observed. For example, when we had short TR and short TE, we had T1 weighting. With a long TR and a long TE, we had T2 weighting. And with a long TR and a short TE, we had proton density weighting. Proton density weighting had the strongest signal strength, so with all things being equal in the signal to noise ratio formula below, proton density weighting will have the highest signal to noise ratio. TR and TE also tie into the type of pulse sequence that is used. Spin echo pulse sequences have longer TR and TEs than gradient echo and so have higher intensities and higher signal to noise ratio than the gradient echo pulse sequences. The formula shows that signal to noise ratio is increased linearly with signal intensity. Note that in this formula I used I for signal intensity rather than S as in the formula above the signal to noise ratio formula shown. And I can point that out to you here. So this is the signal to noise ratio formula, and this is the formula for signal intensity. This S value here is replaced by I in this formula. We saw in CT imaging in a previous lecture that when thicker slices are reconstructed, we are using more photons, and so the signal is higher and the image contrast to noise is better. Similarly, in MRI, once we set the field of view and matrix size we want to use, the thicker the slice, the larger the voxel slice. A bigger voxel slice increases the signal to noise ratio linearly as shown in the lower formula on this slide. And let me pull up the pointer here. So this is the signal to noise ratio formula. So the voxel size is shown here. This voxel size is linearly proportional to slice thickness. So this is just the volume of a voxel. The performance of RF coils depends on various factors. One factor is the geometry of the coil. For small anatomies, a solenoid coil is used to envelope the anatomy, but for most body parts, a surface coil is more practical. Another factor is the sensitivity of the coil to the RF signal from the patient. A rule of thumb for surface coils is that the sensitivity decreases significantly beyond a distance equal to the diameter of the coil. So positioning of the coil is important for determining performance. Sensitivity is also limited by the presence of spurious electrical noise from electrolytes and electrically charged molecules within the patient. Improvements in image performance are achieved through increased signal rather than decreasing the noise. Just as in receiving radio signals in a radio, RF coils must be tuned to the resonance frequency to maximize the signal received by the coil. The resonance frequency of the coil depends on the length, diameter, number of loops, and loading. Resonance frequencies are adjusted by using tuning capacitors or inductors. The magnetic field strength influences the signal to noise ratio of the image by a factor of b raised to the power 1 to b raised to the power 1.5. So for any power larger than 1, we can expect the signal to noise ratio to increase when going from a weaker field strength to a stronger field strength magnet. For example, if the power is say 1.5, then we can expect that going from a 0.5T magnet to a 1.5T magnet will increase the signal to noise ratio by more than 5 times. Signal to noise ratio can be increased by decreasing the bandwidth. The formula shows the signal to noise ratio is inversely proportional to the square root of the bandwidth. So doubling the bandwidth will cut signal to noise ratio by a factor of the square root of 2, which is 1.414. Signal to noise ratio is linearly proportional to the square root of the number of excitations or the number of signal averages. So doubling the number of signal averages will increase the signal to noise ratio by the square root of 2, which is also 1.414. So doubling the number of signal averages and doubling the bandwidth will have no effect on the signal to noise ratio. Image acquisition and reconstruction algorithms impact signal to noise ratio. In order of increasing signal to noise ratio, we have the point acquisition followed by line acquisition methods, then two-dimensional Fourier transform methods, and finally three-dimensional Fourier transform methods give the best signal to noise ratio. Reconstruction filters and image processing algorithms will also affect the signal to noise ratio. High-pass filtration methods generally decrease the signal-to-noise ratio but increase edge definition and so will give a high spatial resolution, while low-pass filtration methods will smooth the image and increase signal-to-noise ratio, but that leads to a decrease in spatial resolution. The appearance of moving fluid in the vascular structure is complicated by many factors like flow velocity, vessel orientation, laminar versus turbulent flow patterns, pulse sequences, and image acquisition modes. Flow signals can be exploited to produce MR angiographic images. We shall see on the next few slides how this is done. Flow voids result from signal loss due to two types of fluid motion. The first is high velocity signal loss, which happens because protons in the flowing blood move out of the slice during echo reformation, causing a lower signal. The other flow void is due to flow turbulence. This is caused by a dephasing of protons in the blood with a resulting loss of the tissue magnetization in the area of turbulence. High velocity signal loss can be useful to produce black blood images for cardiac imaging and vascular imaging. This is done by using a double inversion recovery method, and this involves selecting a slice where there is an inflow of inverted protons that produce no signal so that blood appears black. Flow-related enhancement causes increased signal intensity due to flowing protons. Signal from blood is dependent on the relative saturation of the surrounding tissues and the incoming blood flow in the vasculature. In a multi-slice volume acquisition, the repeated excitation of the tissues causes a partial saturation of the protons in the imaged volume. This is dependent on the T1 and Tr of the pulse sequence. Blood outside of the image volume is not being excited, so the protons are unsaturated. When these protons from outside the image volume enter the imaged volume, they produce a larger signal than the blood in the image volume. This is called flow-related enhancement. Special acquisition techniques like those listed on this slide take advantage of the flow-related enhancement to produce various images. We shall start with MR angiography on the next slide. MR angiography takes advantage of blood flow enhancements to create images. Two techniques used for creating images of vascular anatomy include time of flight and phase contrast angiography, and we shall look at each of those next. The time of flight technique relies on the tagging of blood in one region of the body and detecting it in another. The tagged blood penetrates a volume of tissue according to the T1 used, the velocity, and the direction of the blood. Tagging is done by proton saturation, inversion, or relaxation to change the longitudinal magnetization of moving blood. Two-dimensional slices are acquired to allow for slow-moving blood to penetrate regions of RF excitation of thin slices as shown on the top image on this slide. So this image shows the various thin slices, and as you progress through the image, the bright blood signal should begin to appear. Two-dimensional slices are acquired using gradient echo techniques like GRASS or FISP that produce relatively poor anatomic contrast, yet provides a high contrast bright blood signal. The time of flight MRA views are obtained by projecting the content of the stack of slices at a specific angle through the volume. A maximum intensity projection algorithm is used to detect the largest signal along a given ray through the volume and places this value in the image. The middle image is an illustration of the MIP or maximum intensity projection process. The bottom image is a resulting magnetic resonance angiography image from the MIP process, and that's this image. Phase contrast imaging relies on the phase change that occurs in moving protons such as blood. Phase changes are induced by applying a bipolar gradient similar to what was done in the phase encoding gradient steps we learned about last week. A positive gradient is applied to one view of moving protons and a negative gradient applied to the other view. Moving protons receive a positive phase or negative phase change while stationary gradients are unaffected. By subtracting the second excitation from the first, we can cancel the magnetization from the stationary protons and enhance the magnetization from the moving protons. The illustration on this slide shows the process. On the next few slides, we shall learn about perfusion and diffusion contrast imaging. In the context of MRI, the perfusion of tissues through the capillary bed permits the delivery of oxygen and nutrients to the cells and removal of waste, for example, carbon dioxide from the cells. Perfusion is relevant to functional MRI. Diffusion is the random motion of fluid molecules from a region of higher concentration to a region of lower concentration. Diffusion is relevant to diffusion-weighted imaging. To acquire MR perfusion images, exogenous and endogenous tracer methods are used. The clinically relevant intravascular blood pool agent like gadolinium is used. Functional magnetic resonance imaging is based on the increase in blood flow to the local vasculature following neural activity in the specific areas of the brain. This results in a local reduction in deoxyhemoglobin because the increase in blood flow occurs without an increase in oxygen extraction. Because the deoxyhemoglobin is a paramagnetic agent, it alters the T2 star weighted MRI image signal. Deoxyhemoglobin serves as the signal for the functional MRI. Acquisition techniques that depend on blood oxygen levels, like the blood oxygen level dependent sequence, are used for functional MRI imaging. Blood sequences produce multiple T2 star weighted images of the head before the application of the stimulus. The patient is then subjected to a stimulus and multiple blood oxygen level dependent images are acquired. The images before the stimulus are subtracted from the images after the stimulus is applied, and a resulting color map of areas of the brain with time-dependent activity are overlaid onto a grayscale image of the brain for anatomic reference. This is shown in the slide, in the top figure on this slide. So, as I mentioned earlier, diffusion is the random motion of water molecules in tissues. Interaction of the local cellular structure with the movement of water molecules produces directionally dependent diffusion, for example, in the white matter of brain tissues. A diffusion sequence will use a strong MR gradient applied symmetrically about the refocusing poles to produce signal differences based on mobility and directionality of water diffusion, as shown on the image above in the slide. With a strong diffusion weighted gradient, healthy tissues will have more signal loss than injured or diseased tissues because of free water diffusion in the healthy tissues. An apparent diffusion coefficient map of water diffusion characteristics in healthy, diseased, or injured tissues can be generated and used to evaluate pathophysiology before it is visible on conventional T1 and T2 weighted images. For example, a low apparent diffusion coefficient corresponds to high signal intensity on a calculated image, which represents restricted diffusion as shown on this bottom image. Restricted diffusion in this case has been used as early indicators of stroke. Magnetization transfer contrast is the result of selective observations of the interaction between protons in free water and the bound protons contained in macromolecules of a protein. Magnetization transfer contrast takes advantage of the proton's environment. Protons in proteins are tightly bound and have short T2 decay times compared with protons in free water. By using an off-resonance excitation pulse of 1500 Hz, selective excitation of bound protons is achieved, causing them to become saturated. The magnetization of these bound protons affects the protons in the hydration layer, causing them to become partially saturated. Signals from these partially saturated protons is suppressed. The differential contrast of the flow enhanced signal, as in time of flight MRI, is increased, leading to better image quality of the magnetic resonance angiography sequence. Contrast agents may either be exogenous or endogenous. Exogenous agents are able to freely diffuse into tissues and are hydrogen nuclei like deuterium and tritium, or oxygen-17 and fluorine-19. These are employed in experimental procedures to produce contrast. Gadolinium is the clinically relevant contrast agent used in the hospital. The action of a contrast agent is to reduce T2 star times. Endogenous contrast agents like protons in blood rely on specific excitation or diffusion mechanisms to produce contrast. Here are a few questions to finish up. I will read a question and then wait a few moments for you to think about it and then provide the answer. So the first question, how does the signal to noise ratio in an MRI image change when the bandwidth is increased? So in this question, if you said decreases, that would be the correct answer. So bandwidth is inversely related to signal to noise ratio. So increasing the bandwidth will decrease the signal to noise ratio. Let's look at the next question. Spatial resolution depends on all these qualities except pixel size, sampling bandwidth, RF coil characteristics, or shimming coils. Which of these is the correct answer? The correct answer is shimming coils. So spatial resolution does not depend on shimming coils. Thank you for watching this presentation. Have a good rest of the week.